Okay, welcome to lesson 26. So last week we talked about confidence intervals and hypothesis tests using Z procedures. And this week we're going to shift just a tiny bit and we're going to talk about T procedures. So the first thing we're going to do is introduce what a T distribution is. So, road so far. For Z procedures, when we wanted to do a confidence interval or a hypothesis test, we had these three conditions. So the first, and this is pretty much going to be a condition no matter what kind of methods or procedures we use, come from a random or representative sample. That's pretty much going to always be something that we want to have. Then we want to know, is our sample size large enough that we know the central limit theorem is going to kick in for the sampling distribution of x bar, so that we know the sampling distribution of x bar will be roughly normal. And then this third condition is special to the Z procedures. It's where we have a known population standard deviation. Most of the time, we are not going to be fortunate enough to know this. So know that that is the key difference between last week and this week. So under those conditions, you can do a confidence interval with that equation. You can do a hypothesis test, calculate a Z statistic, use the Z table or R to get a p-value, and go from there. Now we're going to talk about specifically when we don't have this third condition. So we're still interested in doing inference for a mean. We're going to start with 1. So I have a population. I'm interested in finding the mean for that population. The example we're going to work with, we have a car manufacturer that makes sports cars, and they want to know what the average annual mileage is for drivers of their top-of-the-line sports car. They want to be 95% confident in the estimate. And thankfully, we can assume the population to be normal. So what happens? They go ahead, they take a random sample of 10 drivers, and they get these data here. So like this here, this is saying, hey, driver 1 had an annual mileage of 11,501 miles. Driver 10 had 10,392 miles. So checking my conditions to move forward, since from here I want to do a confidence interval. So are the data random? Were they randomly selected? Yes. We have a random sample of 10 drivers. Then we want to know, hey, is our sample going to be big enough that the central limit theorem will kick in? So 10 is not very big. But we know that the population is normal. At least that's what we've been told. So yes, n is 10, but the population is normal. And then, do we know the standard deviation of the population? This is no longer true. So before, we would have used this equation here that had sigma in it. So x bar plus or minus our z star times sigma over root n. But if you don't know sigma, you can't use it. So we can no longer use Z methods for this case. So we're going to start talking about T distributions. So last week when we used Z procedures, that meant that we could assume that the sampling distribution of x bar was normal, and we were able to say, hey, it's centered at this value, it has this standard deviation. We are now going to shift and start using T distributions, which is very, very similar, as you can see in shape, to the normal distribution. These two, they look very similar in shape. However, it's just a tiny bit different. So the key thing here is, if we don't know sigma, we can't use Z procedures, but we can use the sample standard deviation to approximate it. But when we do that, we now have to use what's called a T distribution. So here's our Z statistic. You might recognize the equation. And here, so Z test statistic, T test statistic, the only difference is one uses sigma and one uses the standard deviation from the sample. So when we calculate a t-test statistic, now we have to, instead of using a standard normal reference distribution to find the p-value, we now have to use a t-distribution to find the p-value. So I found this. Surprisingly, I didn't make it. Somebody else did. Mr. T-test. I pity the fool who doesn't know his population standard deviation. So in practice, t-methods are very, very commonly used because it's very often the case that you want to estimate or test the average for a population and you don't know the standard deviation of the population. It's actually very rare that you know the standard deviation of the population. So any scenario where you have sample information only, t is a good way to go if you are testing for a mean. So t-distributions, just a glance here, you can see it's symmetric, it's centered at 0, just like the z-distribution. It is defined by degrees of freedom. So the degrees of freedom tell it how narrow or wide to go. The higher the degrees of freedom, the narrower it gets. So this blue, it's harder to see because they're on top here. That's the standard normal. So that's the normal with a mean of 0 and standard deviation of 1. Here is the t with 2 degrees of freedom. The pink is a t with 9 degrees of freedom. That green in there is 40. So as you increase your as you increase your degrees of freedom, the t-distribution gets closer and closer to the normal distribution. It converges to that normal distribution. So as your sample size gets really, really, really big, the t-distribution approximates the standard normal. One thing, the t has more area in the tails than the normal. I've heard people say, oh, well, they have fatty tails. So the t is a little bit shorter at the peak and a little fatter in the tails. And this is in part kind of due to the uncertainty of like, well, based on having a smaller sample size, maybe you're a little less certain, so you need to have more extreme results in the tails. And so it's an extremely commonly used distribution that's used in confidence intervals and hypothesis testing across the board. It's very, very common. And then I just want to make a note here, degrees of freedom, they're based on the sample size and the number of unknown parameters. So the idea is if I had a sample of n and I had one mean, so I know the mean of this sample, that means that n minus 1 of the observations can vary if I know what the mean is before I know all of the values there. So then there's this question, should I use z procedures or t procedures? So the instances that we would ask ourselves this is when we're interested in looking at a mean. So we might want to test, hey, is the mean equal to is it greater than this value? Or you might want to estimate it. What is the average adult body temperature? That kind of idea. If you do know your standard deviation of the population, immediately go to z procedures. It should be your first choice. We love z procedures. If you meet the conditions, go with z procedures. However, then there's the scenario where we don't know sigma. We have sample information only. So that means that we can't use z procedures because we don't have sigma. So we're going to go ahead, we're going to use the sample standard deviation instead from the sample, and we're going to use t procedures. So that means instead of a z test statistic, we'll have a t test statistic. Instead of a z star critical value, we'll have a t star critical value. So there's a little light bulb. Technically, you could use the t procedures in either scenario. However, if you meet the requirements to use z procedures, they will be a little more accurate more often. you might have a slight increase in type 2 error if you insist on using T methods when you could use Z methods. In general, we use Z procedures first if we can, and T procedures if we can't. It's like a backup kind of idea. So I believe that was lesson 26. So then we're going to go into an example problem.